Howdy. I'm Dr. Pella. I'm the director of the first year chemistry program, and we're really excited to have you all out tonight to learn something about nanotechnology, thermodynamics, and solar energy. So I'm about to introduce our speaker tonight, Dr. Matthew Sheldon. He received his BA from Carleton College in chemistry and his PhD from UC Berkeley, also in chemistry, and performed his postdoc at Caltech in material science and applied physics. He's the recipient of the 2015 Air Force Office of Scientific Research Young Investigator Program Award, the Kanaka Junior Faculty Award, and was selected as a 2017 Inventor Fellow by the Gordon and Betty Moore Foundation. In 2019, he was elected to the Executive Committee of the American Physical Society Topical Group on Energy Research and Applications. And in 2021, he was awarded the Early Career Award from the journal Nanophotonics. His research studies fundamental questions of optical energy conversion related to plasmonic and inorganic nanoscale materials. He also happens to be a pretty great general chemistry instructor. Please join me in welcoming Dr. Matthew Sheldon.
Well, thank you very much, Dr. Pelwa, and thank you everybody for being here. Happy Friday. I'm really excited to talk about this today. This is my passion. This is what I love to do. And I love telling it to you guys what I get to work on and like what actually happens in terms of the research here at the university, okay? So everything I'm going to show you today has been work that was performed by students, PhD students, graduate students, and undergraduate interns in my research laboratory over the past several years. All right. So let me start at the beginning. The big theme of my talk today is energy. And if we want to talk about energy, what energy means, I think there's no better place to start than the definition of energy, really, which is the first law of thermodynamics. We know, based on what semester of chemistry you're in, what the first law corresponds to. It's the statement of conservation of energy, okay? It says that energy can only be converted from one form into another, can't be created or destroyed. We're just interested in how to convert it to useful forms. You might remember the mathematical statement of the first law of thermodynamics, that changes in energy correspond to the capacity to do work or move heat in and out of a system. Okay, and that's really the key idea behind my talk today. Thinking about how we get the energy we want to be using, say from sunlight, to do the things that we need it to do, which is power our society. So that's the key underlying message. All right. Now, let me give you guys some perspective on quite how big the challenge and the scope at which we actually use energy in society corresponds to, okay? I think you guys probably remember some of the units we use to describe energy from chemistry. Maybe we talk about calories or joules. Here's, I think, a helpful chart to think about orders of magnitude of energy and at what rate we use that energy in terms of power, watts per second, which is joules, okay? For different types of things that use energy in our life. Okay, so for example, a toaster, when you're making toast, that's about like 1,000 watts per second of power being drained from the electrical grid, okay? For a point of reference, you being alive, the food you eat, your metabolism, that takes like, that's like 100 watts per second to just keep you clicking, okay? If you've ever been on a flight, you've taken a ride in an airplane, now we're talking another orders of magnitude over the toaster to keep you in the air so you don't crash. We go more, another 1,000 times that, we're talking about the power of like a nuclear power plant, the production that can power a small town or a city, all right? We keep going, well, finally, we talk about the scale of global energy, all right? Many orders of magnitude of power that we have to figure out how to give to people to make society function, all right? Think about that. It's a big number, all right? And it's really important to think about sort of how we use energy and how it's connected to the sort of population and the needs of the people who use the energy in the places where it is used, okay? So what I'm talking about is the energy use per person or the per capita energy use around the globe. It is not evenly distributed at all. In fact, it's highly disparate, as you can see, across the planet. Some places use a lot more energy compared to other places. In fact, there's this wonderful photograph. It's a very powerful image. It's a composite of satellite images of Earth at night. Maybe you've seen this before. And it shows the night sky viewed looking at the Earth. And everywhere you're seeing the lights, everywhere you're seeing the power being used, you're actually seeing essentially wealth. You're actually seeing economic activity. You're seeing prosperity. You're seeing where people have power. You're not seeing Texas in the winter storm, right? You're seeing the actual visualization of how energy gets used. And basically, lighting is proportional, more or less, with the total energy budget of different parts of the world. And that's a good thing, actually. Using energy is good. I'm not here to tell you about the evils of the oil industry or something today. In fact, in the history of life on Earth and the history of the human race, basically comfort, prosperity, and the sort of capacity of what humans can do has always been tied to how much energy they're using. And it has continued in the post-industrial era. If you look at something like GDP, which is the gross domestic product, it's a measure of economic activity and wealth of a country. It is highly, highly correlated with the energy use in that country, okay? And the challenge or the goal and what's exciting and what's possible that we have to think about is we want everyone in the world to have the kind of energy use per person that makes the life that we have in the United States possible, right? We want that to be true for everyone because that enables you to have access to a great education, all the resources that you get at A&M to have the lifestyle that you have here in Texas, right? So this is a good thing, all right, but we got to figure out how to make it possible for everyone because there's a dark side to how we use energy. You've probably heard of this before. So this is the other side of the coin that I want to talk about that really motivates what I work on in my research group. And that is just a show of hands. Let me just ask folks. This is a good question to ask, especially a bunch of Zoomers. How many people think climate is changing because of human activity? All right, your hand goes up. All right, everyone's hands goes up. Okay, this used to be a controversial claim. Okay, not too long ago. And that's really not the case anymore. Lots of people understand that climate is changing because of human activity. The more common response today from folks who don't want to do anything about it is sort of fatalistic, like, oh, we're doomed. There's nothing we can do. Society's going to end because we're all going to die from global warming or something. That's not what I'm here to tell you about today either. I'm going to encourage you to be excited about the prospects for the future. There's lots of good news in my talk today. But my question for you is sort of, how do you support this claim? It's so difficult and so important, especially with like ChatGPT now, right? To make sure that you can actually analyze what's factual and how we understand things that are true about the world compared to things that are just a bunch of hot air or, you know, hot button talking points, okay? And then if we do really understand what are the sources of climate change and how it's coupled to the needs, the energy needs of society, the next question is, okay, so if there is a problem, and yeah, spoiler alert, there's a problem, how do we do it? How do we get around it? How do we solve it? And that's where the solar energy part of my talk comes in, okay? That's what I'm getting to. So let me just give you just a couple more pieces of key information that I think are so helpful so you guys understand like what is the science state of the art that corresponds to actually how we actively understand global warming is taking place. One of the key pieces of data is what's called the Keeling curve, okay? Named after Charles Keeling, who started using a gas anemometer at Mauna Loa in Hawaii to carefully measure the concentration of CO2. He started doing this in the 1950s, and to his surprise, which hadn't been carefully documented before, he noticed that the concentration of CO2 in the atmosphere fluctuated every day. He also noted that it fluctuated seasonally. But to his dismay, what he also noticed is that on the whole, every year, every time he checked, the average concentration of CO2 went up. And it continues to go up. Last year it was there. I think in 2020, we finally crossed 400 parts per million. I think that was the year it happened. It keeps going up. It'll be higher next year than it was last year. Okay. And this is tricky because people had always understood theoretically, even going back to the 19th century, that burning fossil fuels since the Industrial Revolution released CO2, and maybe in some distant future that could affect climate, you know, because people understood the basics of greenhouse theory, greenhouse warming. But his data, okay, this data that he collected has a well-defined slope per year. And we also know quite easily how many tons of CO2 we put into the atmosphere every year by using fossil fuels to power industrial society. And we can calculate that rate. It's just orders of magnitude estimates, the kind of things you guys do when you're doing gas stoichiometry problems, all right? And you can calculate the rate of increase in parts per millions of CO2 per year you expect if it's due to the burning of fossil fuels. And it really well matches the data. So this was sort of like the first nail in the coffin that, whoa, we're actually increasing the concentration of CO2 through human activity. And we've known this really since the 50s and 60s. All right. We also know how to do balanced chemical equations. In particular, I think the combustion reaction is one of our favorites in freshman chemistry, right? We know how we combine our fuel, we combine our oxygen, we make CO2 and water. So if the concentration of CO2 is in the atmosphere is really due to burning fuel, we should also expect the oxygen concentration in the atmosphere to be going down. And it should be going down at the exact molar ratio that we expect based on the amount of CO2 forming. And indeed, that has also been confirmed over and over again. So this is how we know that human activity is the source of CO2, independent of all the other complicated factors that people know about contribute to the total carbon budget in the atmosphere. And it's a very complicated global system, but this is how we know it's from human activity, one of the ways we know. Okay, so how does this connect to climate change? Well, understanding effects of climate are also fairly difficult and sophisticated sort of modeling problems, largely. But in fact, the reason climate changes in response to carbon is a pretty simple energy balance on the whole, on the average, how we can figure out the basics of the picture. And it comes down to probably what you've heard before, the greenhouse effect. CO2 goes into the atmosphere, the CO2 from burning excess the release of carbon dioxide from fossil fuels. And it's a little more complicated than probably the picture you had when you were, that you might have heard when you were younger. It's actually the concentration of CO2 in the upper atmosphere changes what the temperature of the whole planet needs to be in order to be in a radiative equilibrium with the light that's received from the sun and the light that we re-radiate back out. So the point is that small differences in the concentration of CO2 are what actually change the balance. It's kind of like we're on the head of a pin in terms of where the temperature is compared to the amount of CO2. So again, it's small changes in carbon concentration, parts per million, but it's the change in temperature that we get from that is also actually relatively small in terms of the Kelvin temperature scale. We're talking a couple degrees compared to like 300 Kelvin for small changes in parts per million of carbon. But those little bits of degrees, well, okay, this is the thing. Now, this is not a doom and gloom talk, but this is what you really want to have internalized. So we have great evidence in the climate record. This data is actually from ice cores that have little bubbles, and so we can monitor the gas concentration in those bubbles going back hundreds of thousands of years, okay? The average global temperature is highly correlated with changes in carbon concentration on the order that I'm talking about, small differences in parts per million. Okay, I'm almost done with the gloomy part, I promise. But I want to draw your attention to this. This is the data from the Mauna Loa, the Keeling curve I just talked about. Since 1950, compare that to the range we have. This is what makes people nervous. This is what gave me an anxiety in graduate school when I first actually internalized and understood what this meant, okay? If you want to be depressed, hang out with climate scientists because they understand this better than anybody else, all right? So should I be worried? I'm a little worried, but that's what motivates me into this research. That's why I'm excited to talk to you about it today, okay? So last thing I'm going to say about this is I am not a scientist who specializes in global climate change or atmospheric chemistry. And there are many, many different types of research communities that have been working on this problem for literally decades, to come to a conclusion about what we can expect in the coming decades for climate change, okay? There's business as usual, and this is really bad. 4 degrees Celsius business as usual means like agriculture stops functioning for staple crops in the civilized world. Disaster kind of scenario. And there's a scenario where we can do what we want, where we aim for what's in all these international climate accords and things. I'll talk about this. And the good news, the first piece of good news, is that we are not on this trajectory anymore. Since past several years, maybe a decade or so, we're deviating towards good behavior. And there's a lot of factors that contribute to that. So that's the first piece of good news. And I'm going to end my presentation today telling you how we're getting closer and closer to the scenario we want. Okay? All right. So that's the good news, everybody, because there actually is a path forward. It's a miracle, actually, that has come together since the 1970s that allows it for me to say confidently that solar energy is actually the answer here. It's a complicated problem that needs many, many people working together in politics and economics and engineering and finance and et cetera and et cetera. But solar energy is what can get us there. All right. And that's because the solar energy resource just dwarfs everything else available to us. The size of these circles tell us how much is available for us to just take advantage of. And if you compare the fossil fuel resources, for example, compared to our world energy consumption, you can see solar can satisfy our needs. All right. So then the question is, what do we do? How do we get here? And that's the rest of my talk. So here's the first question I have for you guys. If solar energy is so great, why isn't it already the way we power society? Actually, it was up until the Industrial Revolution through the way we grew food and fed it to livestock to like move plows and things. Okay, but fossil fuels are really cheap and they're really concentrated. The reason we don't use solar energy right now at the scale we should be or need to is very simple. It's because of the cost. It's still because of it's expensive. All right. If you look at the cost of electricity that comes from a solar source, a solar power plant, or a solar cell that's on your roof, the total cost comes down to things like the land that you have to pay for, the people you have to pay and train to construct it and install it. All right. Lots of other costs associated with, taxes and legal stuff that I don't fully understand. All right. But the big chunk, approximately half of the cost of a solar cell and solar energy comes down fundamentally to the materials cost and the expense of actually procuring and manufacturing the technical component that converts the light that's absorbed into energy. Okay. So all of the cost of all of these things become less and less relevant if your solar cell becomes cheaper to make, okay, which is one factor, or if your solar cell can produce more electricity based on the amount of cost that you spend to make it. Those are the economics of solar energy. That's the only thing a banker cares about when they finance a solar investment, okay? And so then here's my next question. If solar cells are literally made from melted sand, and they are because they're primarily made out of silicon, okay, which is melted sand, then why are they so expensive? Okay, well, the answer is simple, really. It comes down to the second law of thermodynamics. I talked about the first law of thermodynamics. So here's how the second law rears its ugly head. Actually, this is like one of my all-time favorite Simpsons quote. If you know the episode, Lisa makes a perpetual motion machine because they cancel school and she's bored at home. All right. Okay, so the second law of thermodynamics says entropy increases for any spontaneous process. Do you remember that? You've probably gone through this, or even if you're in 120 right now at this point, right? This actually puts limits fundamentally on how well a solar cell can work. And I'm going to talk about that. All right. That's because if we're going to take energy from sunlight and use it to do something that we need, like power your electric car or cook your, Pop-Tart in a toaster, it actually has to increase entropy. Do you guys remember this sort of mathematical statement of the second law? Have you guys seen this yet in your classes? It says the free energy change of some chemical process or physical process or a solar cell, the free energy, which is the energy you can use, the Gibbs free energy, has to produce entropy, all right? And the amount of free energy that we get, how much we can use to do something we need, is dependent on the magnitude of these terms, all right? And I'm going to come back to this. If entropy goes up or down, or if the process is endothermic or exothermic, this impacts how much free energy we can extract from the solar cell. Okay. And there's a corollary of the second law of thermodynamics, which is called the Carnot efficiency. And we can analyze the Carnot efficiency in terms of the fundamental temperature of the sun and the earth, okay? The Carnot efficiency is as I said, the corollary of the Gibbs free energy that tells us if we have some kind of process and we're trying to extract free energy from it, the maximum amount of free energy that's possible actually depends on the temperature difference between the hot side and the cold side of some kind of thermodynamic heat engine. Okay, now this is a very abstract version of a solar cell. This probably doesn't look like the one you're familiar with. I'm imagining it's a PV work cycle where we have some gas at the temperature of the sun and some gas at the temperature of the earth. Nonetheless, this actually puts the bounds on the maximum theoretical efficiency that a solar cell can operate at. If you assume the temperature of the sun is what powers it and it's sitting on the surface of the earth. Now for space-based solar, that cold temperature goes lower and so you get higher efficiency, okay? But my point is that the reason solar cells are expensive is because of this. Solar cells are expensive because the way they work, the best current designs we have, actually have a very low thermodynamic efficiency. They work at about a 33% conversion efficiency. At their very best, even if they work perfectly, they cannot approach this Carnot efficiency, all right? 33%, so that means a third of the power from the sun that hits them is all they can use. The rest just gets wasted. That's why solar cells are still expensive, okay, compared to other forms of energy. So just to summarize this a little bit more, here's our heat engine, the solar cell powering a happy planet. And I have this chart here, which imagines the maximum amount of power we could extract from the sun to do the things we need at the Carnot limit, this limit due to the second law of thermodynamics. It's about 95%. And then I have all these chunks of color, okay? Each one of these little bars correspond to a fundamental microscopic physical or chemical process in how a solar cell converts the photon it receives from the sun into electrical power that maybe you use to charge a battery or make a fuel, whatever you want to do. And what I'm going to talk about a little bit are some of the details that define these little steps in this curve, what takes us, what we need to get to this best possible conversion efficiency from a solar cell, which is what we need to make it as cheap as possible to actually solve all of our societal woes, okay? And that's what my research lab does, okay? We think about these microscopic details in terms of how a solar cell operates at the chemical level, at the microscopic level. We think of it in terms of physics. We think of it in terms of chemistry. And this is the team. There's some undergraduate researchers here. This is Anna Champ right here. I don't know if you know her. I'm hoping I'm not embarrassing her. And what I'm going to talk to you today is how there are really exciting opportunities in how we've gotten very good at structuring matter at the atomic scale and the nanoscale for fundamentally changing how it interacts with light to reinvent that equation or that thermodynamic limit. What I tell my students in our laboratory is we don't violate the laws of thermodynamics, we just sort of work around them because we change the underlying assumptions for how a solar cell works and how it interacts with light in order to get closer to that Carnot number, that Carnot limit of 95% I told you about before. Okay, so before I can tell you the cool, exciting new research, I had to tell you a couple more foundational facts about how solar cells work. First thing, Solar cells are made out of semiconductors. Maybe you've heard the word before. Semiconductor is in contrast to something like a metal, which is a conductor, or something like a ceramic or a piece of glass, which is an insulator. A semiconductor is somewhere in between, and they're characterized by having an energy band gap, okay? And I'm gonna talk about how this makes sense. And actually, can I just get a show of hands? How many people actually went through molecular orbital theory in their class when they went through bonding? Okay, I know we went through it in my section, okay? All right, so many of you have, many of you haven't. But we all know that atoms have orbitals, right? If we're talking about one atom, it has this energy state for its electron. We might call it the s orbital. We might call it the p orbital. We remember that, right? Okay. The idea of molecular orbital theory is that we take advantage of the wave-like properties of electrons when they're in orbitals around atoms, okay? And when we make a chemical bond, we can think about the interference between the orbitals of two atoms. And the red and the blue color is representing the 1s orbital of a hydrogen atom here. And if you remember the Schrodinger, there's a real part and there's an imaginary part. That's just what the two colors are telling us. Not an important detail. But they can interfere constructively or deconstructively to give two new energy states. We call this the sigma and the sigma star, or the bonding and the anti-bonding orbital. But it's really how the orbitals of atoms mix together to form orbitals, okay, that characterize molecular states. We call these molecular orbitals. And then we can put electrons in these molecular orbitals just like we would when we use the Aufbau principle and Hund's rule and Pauli exclusion to describe the atomic orbitals, okay? And this process iterates. I just showed you how we get a bonding and an anti-bonding, sometimes called a HOMO and a LUMO, for two hydrogen atoms coming together. But if we take more and more atoms, that mixing can happen more and more, and we get more states if we have like 4 or 6 or 8 or 10 or 12, until eventually we get a mole's worth of atoms bonding in a solid, like a piece of silicon, okay, like a continuous hunk of semiconductor. And these states instead become what we call bands. An electron can have any energy in this region, it can have any energy in this region, but there's what we call a band gap where they're not allowed to have any energy. This is the fundamental distinguishing feature of a semiconductor. It has a band gap that comes fundamentally from sort of bonding and anti-bonding type orbital interactions in the extended solid. Okay, that's the first fact. This is what a semiconductor is. Okay, next fact. Solar cells use the photovoltaic effect. I'm going to call that PV. If I say that without thinking, that's what I mean, photovoltaic. All right. So because there's a band gap in a solar cell, this means that there's a constraint on the wavelengths of light that the solar cell can use to excite and move electrons between states. This is just to say the band gap has a certain gap in energy. And so if we're going to excite an electron between one of these states to another state, it won't work unless we give it light that's sufficiently energetic to jump the gap. And that's how a solar cell functions. It takes light from the sun, the light from the sun that's energetic enough to excite an electron from here to there, then gives that electron a little bit of extra kinetic energy, a little bit of chemical potential. I don't know if you would have learned that in chemistry yet, but basically some free energy the electron has, and we can just wire that up and collect it before the electron relaxes back down. That's the fundamental mechanism of a solar cell, what we call the photovoltaic effect. And this is why solar cells are lame. This is why they don't work that well. Because, first of all, solar cells can't absorb any color of light that has a wavelength that's not energetic enough to cause an electron to jump the gap. So low energy infrared light is useless. Low energy red light might not be sufficient to excite an electron. It can only use light that has enough energy to jump the gap. So I have here plotted the solar spectrum as a function of wavelength I don't know if you guys remember what a black body spectrum looks like, but basically the sun is a black body at 5,600 degrees Kelvin. And then these little dips are just atmospheric absorption lines from things like water and carbon dioxide, actually. And what this means is, based on the energy of the band gap, all of this sunlight, we don't get to take advantage of. So that's the first problem with a solar cell. It just doesn't absorb a lot of the light that hits it. The other problem is because of this band gap, okay, if you excite an electron that has more energy than the band gap, let's say it absorbs light and it excites an electron way up here, well, the problem is because we have to wire up the solar cell, all the energy the electron has up here is useless. All we can do is collect the energy with electrons at the band gap energy. So there's wasted energy. It turns into heat. We say it's thermalized. So basically, any light that's above the band gap energy is underutilized. So these two factors mean that basically the solar cell can really only use like one color of light in terms of the energy that it gives to the to the electrons that you're going to use to do work. That's the reason they fundamentally have a bad thermodynamic efficiency. And so there's this trade-off, which is called the Shockley-Quasar limit. It's the thermodynamic model for how a semiconductor solar cell works based on the photovoltaic effect, which is really just saying, okay, we want a big enough band gap so that we get enough free energy from the electrons, but it's got to be small enough so that we absorb as much light as possible. And we look at the dependence of band gap energy. Electron volts is just a unit of energy, like any other unit of energy. And we see there's a particular value where it peaks at about 33%, corresponds to a band gap of about 1.2 EV, which happens to be almost identically the band gap of silicon. Okay, so what this tells us is also kind of fundamentally interesting. Silicon's already the best possible a solar cell can be. Silicon solar cells work at about 30, the best cells work at about 30% efficiency. They're getting close to this thermodynamic limit because they work as good as they possibly can. All right. And so the reason they're inefficient is because these fundamental limitations of how they interact with light. That's why solar cells are expensive. You couldn't make them better anymore. They are at this limit in terms of their performance. So if we want to make cheaper solar energy, if we want to make more efficient solar cells, if we want to power society with sunlight, we have to figure out how to make solar cells get past this problem. We have to figure out how to get them cheaper and producing more electricity. And we're doing that. Okay. So here's a solution. The rest of my talk, I'm going to tell you about a particular scientific research project in my laboratory that's been going on for a few years that's addressing this particular problem, which is just one of the several problems I haven't chosen to talk about today that are connected to how to make solar cells better. The idea is, if the problem is that we can't absorb light below the band gap, and we're wasting the energy of light above the band gap, okay, well, what if we just change the color of the light? What if we just change the energy of the photons in a way that's optimized for the band gap of the photovoltaic? This is a process called luminescent up conversion or down conversion. But the idea is you take the spectrum of sunlight that you get from the sun, and you put a special coating on top of your solar cell that is like fluorescent paint, or what we say like photoluminescent, like glow. You know, if you've ever played with like black light paint or something like that, something that absorbs light from the sun and converts it into luminescent light, but at an energy that works for the photovoltaic's band gap optimally, so that you can get around this thermodynamic limit. And so here's just an example. This is a thing. It happens with some efficiency, low efficiency, not enough that's good enough for solar yet, in certain like molecular dyes, organic dyes. Here you can see a green laser is going through this flask and making blue light. This is actually very analogous to what I'm going to show as I continue. So low energy green light comes out as high energy blue light. Same idea here. Low energy red light is absorbed and it's luminescent as blue light. If you could basically chop up the solar spectrum and make it the colors you want, you can make a solar cell that gets theoretically close to that Carnot number. And we're working on that problem in my research group. Okay. And the way we're getting there is with nanomaterials. And what are nanomaterials? Nanotechnology. Why are they interesting? How can they help? And so actually, uncredited, this is an undergraduate researcher from my lab holding the tweezers on this really cool sample. He's now, I think, working for Samsung in Austin. This was a film of these types of semiconducting nanocrystals that were in a solution. I'm going to talk about what all this means, embedded in polymer and cast as a film that we were then trying to apply to solar cells to do exactly what I just explained. Convert the color of light to make the cell work better than the theoretical thermodynamic limit. Okay, but so let me tell you like the why of nanomaterial, or the what, like what are nanomaterials? So conveniently, I already taught you guys what a semiconductor is in terms of molecular orbital theory, okay? I said we can start with atomic states and we can end up with bands when we go to macroscopic sized chunks of matter. But what is very exciting, and what happened when I was a little kid in the scientific research community, is figuring out how to precisely engineer materials that were somewhere in between in size. These are sometimes called quantum dots, because by controlling their size and their shape and many other properties I won't get to talk about today, you can fine-tune this electronic level structure inside the material. And many other properties, not just how they absorb light based on their band gap energy, but many different properties depend on the size of a material that you can tune. And so this is an important fundamental point that we don't teach you guys that much in first year chemistry, which is size dependence. How a material is structured and its shape and its size is a fundamental and distinct chemical or physical property. And the reason for that is that it constrains the electronic wave function. So just like the orbital around an atom depends on how the electron sort of oscillates and its resonance in its energy structure, we can do that in a more sophisticated way now by constructing and engineering materials where we control the quantum nature of the wave function of the electrons. And that's what's powerful, because if we can actually start to understand this and make these electronic wave functions do exactly what we want, maybe we can get around the limitations of conventional materials. That's the thinking behind the research in my laboratory and why we're interested in nanomaterials. They are, so we say, tunable quantum platform. So how do we make nanocrystals? I think this is a fun and interesting part of the research, all right? Basically, nanocrystals are a very controlled type of precipitation reaction. You remember figuring out your solubility rules and whether something will it precipitate or will it be soluble? Well, basically, we put special salts and we inject them into high temperature reaction flasks in a controlled way so that as the salts start to precipitate and crash out of solution, there are surfactants, we say, or like soap molecules, things that have a polar side and a non-polar side that interfere with how the crystal starts to agglomerate and would precipitate out. And instead, these little precursors break down as the temperature is initiated, the crystals start to precipitate, but we interfere with that process and we stop the size of the crystal growth in a really controlled moment in time in the reaction. And that's how we can precisely define their size. And in this image, what you can see is this 10 nanometer like black shape. But what you're observing, these contrasts and these well-defined rows and columns, those actually correspond to the positions of the atoms in this nanocrystal. And the way it's being imaged is in a special tool called the transmission electron microscope that basically gives contrast where the electrons scatter with the atoms inside the material, okay? So we're really good now, as a field, in terms of our ability to precisely control these quantum materials to imbue them with the properties that might be interesting in my lab for solar energy. Okay, this is just I'm telling you, this is a material we work with. This is called perovskite, all inorganic perovskite nanocrystals. This is a hot material right now. in the biz because it turns out to be probably the best solar material we've ever discovered. It's just really, really good at being a semiconductor and having a photovoltaic effect that's very close to the theoretical best that it could possibly be. Okay, and what's cool here again, more TEM. We can make these. Here I'm showing off how well we can control the band gap, but there's many things that we can control very precisely that are interesting for this problem in solar energy, okay? And I want to make the point that there's a lot more we can do depending on what are the needs of our application. And I think this is one of the things that's really fun and exciting about this research area. There are new things we can do every day, okay? There are people in my lab who are sort of mixing chemicals in a sort of thoughtful, systematic way to try to make new properties that we can take advantage of, all right? Okay, so once we make these, we integrate them into materials to have these applications I talk about. And what's cool is this is really a sort of a next generation way of thinking about how to control the properties of a material, because we're defining it at the atomic scale through this self-assembly process and then building more and more complicated structures out of it. This is what the future is going to definitely look like in terms of these types of technologies. These are already what's used in like quantum dot display screens, if you have any of those like fancy TVs or phones, for example. Okay, so here's why we're really interested in them. We actually, my laboratory is one of the main groups that discovered this property that these perovskite nanocrystals are very, very good at this process of luminescent upconversion, okay? Here's a fun cartoon graphic we got to make for the cover of a fancy journal, okay? Showing that when you shine green light on these nanocrystals, they absorb it, and then they re-emit that light at a higher energy. Okay. Did everyone get out your clickers? I have a question. So here's the process. A green photon comes into my nanocrystal, okay? It's absorbed, and then it's re-emitted as a blue photon, okay? Here's my question. This is a spontaneous process. We shine it, I have a green laser pointer. If I had my nanocrystals right now, I could hold them up, I shine my green laser pointer, and it'd be glowing blue, okay? My question for you is, in this spontaneous process, is it endothermic or exothermic? Does the photon energy go up or does it go down by interacting with the nanocrystal? Let's get a show of hands. How many people think this is endothermic? Okay, I see some good hands. I see the professors raising their hands. How many people think this is exothermic? All right. The process, now this is the challenge of thermodynamic questions, defining your system. But the system is the photon going in and the photon leaving at a higher energy. Our products minus our reactants, higher energy minus lower energy. This is endothermic. Okay, good job. Friday night, right? So we have an endothermic process. Let's go back to the second law of thermodynamics for a second. So what does that mean if this happens spontaneously? If delta H is positive, what must be true about delta S, our entropy? We must have entropy increasing. And in fact, that's the only way we get free energy. This is the only way this works. To make this happen, it turns out, and this is a big, big factor in all the research in my lab, is we're thinking about how to control and manipulate the entropy of the radiation field. We think about the photons in many of the same ways in chemical reactions or solution chemistry that we think about the free energy and the entropy of the chemicals in solution. We think about that like for the photons as well. And it applies because the laws of thermodynamics don't care if you're a chemical or a photon. They still apply. Okay. Now, here's the other really interesting piece of this. This is an endothermic reaction. Photon comes in at low energy, it leaves with higher energy. How does that happen? Where does that energy come from? The nanocrystal gets colder. This process spontaneously extracts thermal energy from the environment and converts it into higher energy photons. That's why it can make the solar cell work better, because it's turning thermal energy into electricity at the band gap energy. So this is like fundamentally changing the thermodynamic equation on how well the solar cell could work. Very exciting possibility, and it totally does this. I mean, that's the crazy thing. The first time we saw this, we were just like, no, the detector must be broke. There's something wrong with the spectrometer. Go redo your baseline. No, it's like, there must be an issue. And it took a long time for us to be convinced that this was actually what's going on, because it's so weird. Okay, so there's a whole team of people in my lab that are now exploring different aspects of this and consequences of this, both in how we can sort of synthesize the material and optimize it and understand this process more fundamentally, and connect it to things in terms of the structure that we can control and think about the way we think about it as a chemist or as a material scientist or as a physicist, okay? And we're also trying to actually turn this into the application I specified, where we're going to put this material to convert the solar spectrum of the light from the sun into something that makes it work better in the solar cell. Okay, and here's some of the team who have been working on this project in my lab. Okay, so I'm going to tell, I think there's time for one more little story before, right? Yeah, okay, good. So this is a project that was proposed by my student, Kylie. She's a graduate student. She's going to get her PhD. And when you go for a PhD, you have to propose a project topic that is your dissertation that you're going to work on, you're going to do experiments, you're going to learn about. And when you're done, that's how you become a doctor. That's what your PhD means, that you've achieved that scientific goal. And she has a hypothesis based on this project, based on interpreting this fundamental physical process, because it is thermally activated, which is to say, we know that this is upconverting light because it's extracting thermal energy from the nanocrystal, okay? She proposes that we can use that to get insight into the mechanism. In fact, it's a little bit complicated. If you don't follow this too much, don't worry so much, but I showed you before that we have this semiconductor band gap structure. Well, there's this very special phenomenon that can happen in materials like these perovskites that we're working with, that when you excite that electron into the nanocrystal, because it's charged, it sort of distorts the electrostatic interactions that make the structure of the crystal. And that's called a polaron. It's like it's sort of like if you put a bowling ball on a mattress and it kind of distorts the mattress locally. It's kind of like that, but where the electron is moving around inside the crystal. And that changes the energy level. So instead of just being this simple band structure with a band gap, like I said before, she proposes that what we actually have that's giving us this upconversion process is that our band gap structure is contorted into something that looks more like this, where somehow there's a little state that we're exciting into at a lower energy, and then the thermal energy excites electrons out of that little state so they can recombine at the bigger energy of the band gap, okay? That's the hypothesis. I hope that kind of came through. This is a proposal for the state structure that gives rise to low energy in, high energy out. Okay, I'm gonna tell you one more thing. How many people have gone through Arrhenius law yet and rate equations? Oh, good. Okay, great. This is gonna go great. How many people remember reaction coordinate diagrams? What? There's gonna be a pop quiz now. So remember, we had a thermodynamic perspective for chemical states. We can have an initial state, we can have a final state, and we can analyze the energies of that. But that doesn't tell us anything about the rates of a chemical reaction or the kinetics. That's determined by what we call the energy barrier. We have to have thermal energy in order to reconstruct the positions of the atoms. They have to kinetically move around, they have to collide, and there's some energy barrier to that before they can get to their final state. Remember this? All right. And due to kinetic molecular theory, if we increase the temperature of the system, we give more energy to the molecular sample in order to overcome that barrier. Remember that? And so we find the Arrhenius law or the Arrhenius equation, which says that the kinetics or the speed or the efficiency of any chemical process is increased if we increase the temperature. in a very well-defined mathematical way. Okay, so we can plot the rate of a chemical reaction versus inverse temperature, and that tells us the magnitude of the activation energy. Do you remember that? This is the last thing I'm going to say about it. Okay. So Kylie has done that. We know that the nanocrystals turn thermal energy into light. So she does an Arrhenius analysis. She plots the intensity of the light that we receive, which is correlated to the rate that it's created at, as a function of inverse temperature, and she can solve for the activation energy, how much thermal energy is required for this upconversion process to take place. She just puts the nanocrystals in a solution, she changes the temperature, and she measures the intensity of the upconverted light. And what did she learn? Well, the slope of the activation energies as a function of the difference in the incoming and the outgoing light is not 1. What am I talking about? Basically, this. You might expect that the amount of thermal energy it takes to upconvert a green photon into a blue photon is just the difference in their energy. But that is not true. There's an activation barrier. We have to put in more than just the energy difference in the photons in order for this to occur. We can measure that, and it shows us that her hypothesis for this state structure is very, very well supported by the behavior we observe in the Arrhenius law. So I just wanted to share that with you guys, because you might think when you're learning the Arrhenius laws that this is like this weird thing from a Dutch chemist from like the 1600s, but actually we're actively using it on a daily basis in my research group today to do cutting edge science. So it comes up. These are why we're teaching you these things. Okay. So where are we going with this? Well, this is a big process. There's many people working on it, and we're developing the chemistry and the material science, and we're trying to develop the technologies. We were able to prove that you can actually do optical cooling. You can make devices that when you shine light on them, they get cold, and that's what I'm showing here. And we're working towards developing other types of technologies besides just improving solar cells that can really take advantage of using light power to get colder. Wouldn't it be awesome if we can just make a paint that you paint on your garage in Texas so that in the summertime, instead of getting hot, it gets cold? Wouldn't that be great? Yeah, that's one of the things that we're working on based on this fundamental phenomenon. Okay, so I promised I would end with good news, and I've got 2 minutes of good news. Do people want to hear good news before we wrap this up? Okay. All right. And this is why I'm optimistic and excited about this research. All right, so I showed you this maybe not good news plot a second ago about good behavior and business as usual. And I said, thank goodness we're not on this trajectory anymore. We're much closer to here. Why? How are we getting there? That's what I'm going to share with you right before I'm done. Well, the very good news that happened just last year is we passed the Inflation Reduction Act. I cannot express to you how happy that made me as someone who worries about climate science. In my entire life, the United States has never had any serious policy change in order to reverse the effects of increasing carbon concentration in the atmosphere. And now we have, and it's really substantial. It's going to make a real difference in a way that just wasn't possible until this year. So for the first time in my life, that little ball of anxiety about global warming is suddenly like, wow, there's a path, I can see it. And I hope you guys can appreciate how important it is to have real legislation that goes through that makes a difference to the things that will impact your life. Okay. Other good news. There's something called an experience curve. Maybe people learned about this in one of their econ classes, but basically, the price or the cost of a good to manufacture decreases exponentially as the rate at which it's produced increases. Basically, it's called an experience curve because companies learn how to make it cheaper at scale. This is why, like, you can buy things on Amazon a lot cheaper than at your like local mom and pop store. Okay, that's one of the things going on here, or Walmart. Okay, this is the example of the Model T. The price dropped orders of magnitude in the first 20 years of production as it became like the ubiquitous thing that defined the United States. Okay, check this out. This is the experience curve of photovoltaic modules based on semiconductors from silicon. I just can't express. This is a log plot, by the way, guys. So since the 1970s, before I was born, the cost has gone down for a solar module by many orders of magnitude. And here's the other cool, exciting thing about this. This trend isn't going away. Every day, solar cells get cheaper and cheaper and cheaper. So I said they are too expensive. Well, look at this. Something amazing happened in 2020. Does everyone remember there's some big news in 2020? Well, yeah, the big news was solar energy reached grid parity. For the first time in history, solar energy was cheap enough that it is now and remains the cheapest source of electricity. That is so huge. It's a miracle. No one ever thought that was going to happen 2 decades ago. And now it's the reality that we live in, okay? And it's so exciting to think about what that actually means. We suddenly have a source of energy that's way more abundant than fossil fuels, and now it's also cheaper. That is going to fundamentally change the structure of society. And it definitely will allow us to actually deal with global warming. That's the hope, that's the goal, okay? So my last slide is the slide that I always look to when I need inspiration. When I'm down at work or someone's complaining about their grades. So this is a chart that lists the record efficiency of different solar cell technologies for any year. And they've been plotting this chart since the 70s. And it's provided by the National Renewable Energy Laboratory in Boulder, Colorado, okay? There's so many things I could tell you about this chart, okay? But one thing to tell you, do you see this in this region in the middle in the 90s where everything's kind of flat? That's when conventional photovoltaic technology reached the thermodynamic limit. That's when everything kind of flatlined. But check this out. What do you notice these days about the trends? They're all getting more efficient. Solar cells are always getting better. And it's based on just hundreds and thousands of scientists and researchers and engineers around the world working on little problems, trying to figure out little ways or big ways to make a crack at this. And so the final thing I'll say is, what do you notice about the biggest number on this plot? It's kind of small. It's not 93%. It's not 95%, okay? So this is the thing we get to look forward to, I think, and what makes me really excited also is this is just going to keep getting better too. So everything's coming together. Like there's actually an amazing future for solar energy. It's going to be a part of our lives, and that makes me really happy, okay? So I want to thank everybody. I want to thank my group. I want to thank you for your attention. Thank you. What's that?
Dr. Sheldon will be available for a few questions if you'd like to come up to the front. Thank you all for coming out tonight.